Welcome to another video podcast. In this episode, we're going to be taking a look at another substitution rule problem. This problem is a little bit more difficult and involves what in class I've called an inverse substitution. So if we take a look at the integral on the screen, the first thing that we probably notice here is that the expression under the square root is causing us a little bit of problems. It'd be much easier if we could simply take and let u be 3x plus 5. So this is probably the the first approach that you would make for this problem. Now if I did that, then when I calculate the differential du, that's going to give me just simply 3 dx. And if I compare that with what's in the problem, I immediately notice that that's not going to work. The reason that it won't work is because I have no way of accounting for this x here. What I need is the differential to be x dx, not 3 dx. Well, there's really no good way around that. And in fact, the only way that you can really do this problem is to go and instead of solving for u, instead of making your substitution in terms of u, you should also do what I called an inverse substitution, which is to express the substitution in terms of x. Let me just go ahead and implement the substitution that we have, and I'll show you why this is important. So if I go ahead and put in everything involving my substitution, I'll replace 3x plus 5 with u, and I'll replace dx with, if you look here and solve for dx, dx is du over 3. So at this point, this is what I have in my problem. That pesky x outside the square root is the one that's causing his issues at this point. But I can solve for x. If u is 3x plus 5, then that means x is u minus 5 divided by 3. This is what I referred to in class as being the inverse substitution. In mathematics, you should always be aware that anytime there's an equal sign involving multiple variables, you can always express it in terms of the other variable. You're not bound to just saying that this is what u equals. This also gives a condition on what x equals. So if I update the integrand with that value of x, then I'm looking at u minus 5 over 3 times the square root of u. And then I have du over 3 from my earlier differential. Now if I continue on with this, I need to clean it up a little bit. If I take the two constant 3's, I can pull them outside the integral as a 1/9 because everything here is multiplied. Nothing's added. So I can pull this out as a 1/9. And then this is starting to look a little bit better. I have u minus 5 times the square root of u du. It's still not in a good form to take an antiderivative. So to get around that, what I should do is think about distributing the square root of u. If I do that, I get u times the square root of u, which is u to the 3 halves, minus 5 u to the 1/2. Which is just the square root. Now it's in a much better form. I can actually take the antiderivatives using power rule at this point. So let me just illustrate this off to the side with u to the 3 halves. Remember, u to the 3 halves, if I take its integral, that's equal to, I increase the power by 1, which would be 5 halves, and I divide by the new power. Well, we'd rather represent this as 2/5 u to the 5 halves. So that's how I'm going to handle this. This will be 1/9 times, when I do the anti-differentiation step, I get 2/5 u to the 5 halves minus, here it's going to be 3 halves, which when flipped gives 2/3. So it should result in 10/3 u to the 3 halves. And because it's an indefinite integral, I'm going to add a constant. Now it's probably best to give a final answer where I've distributed the 1/9 back in, so if I quickly do that operation, I'll get 2/45 u to the 5 halves. 1/9 times 10/3 is going to give 10/27 u to the 3 halves plus a constant. So there's a good final answer for this problem. Thank you for watching.